I want to continue examining functions as power series. And to do that, I want to start by looking at our term-by-term derivative idea again. So here's a power series for some function. I know this is going to have some radius of convergence. For the moment, I'm going to assume that it converges on more than just a single point. I'm going to assume this converges on some interval with a radius that is positive. And the reason I do that is because this function is going to be continuous and differentiable in that interval. If it was only defined at a single point, then I couldn't take derivatives. And I want to take derivatives because that's what we were doing on Monday. But even before I do that, I don't know what those coefficients are. I don't know what the Cn values are. Except I do kind of know something. I know that you can also write this power series out like it was a polynomial in increasing orders of, rather than x minus a. With that in mind, what's the value of f of a? Yeah. And that means that all of these terms and every term above that is going to be a 0. Okay. Let's take a derivative here. The term-by-term derivative. F prime of x would be the sum n equals 0 to infinity Cn n x minus a to the n minus 1. That was what our term-by-term derivative idea was. I just took the derivative of this part. Chain rule gives me a 1, so I don't have to really multiply by anything on the end there. But if I take the derivative this way, that would be the same as writing this out. What's the derivative of just C0? Great. Here, this is x minus a to the first. Derivative of x to the first is just 1. Stuff to the first, I take the derivative of the inside, but the derivative of the inside is also 1. So that's just C1. And here, I get 2C2 x minus a to the 1, and then 3C3 x minus a squared, 4C4 x minus a cubed, and more. I'm actually going to go ahead and write a 1 next to that CA to remind me that it came from the x minus a to the first term. That's the n here. With me so far? Put in A. What happens? Right, because everything else becomes a 0. Now, wait a second. I now know, without actually knowing what the power series terms are, I can start to figure out the coefficients, C, looking at derivatives of F. Do it again. F double prime. I'm going to use the written out version. I think that's easier, but I've written the term by term differentiation up there. I just did the power rule here, brought the power down, subtracted 1. Derivative of C1 is 0. The derivative of the linear term is a 1. The derivative of the quadratic term is going to have an x minus a to the first. Oh, wait a second. Right? So that's gone. Again, since I got this here, I'm going to put a 1 there. Right? I got it from the x minus a to the 1 term. So I'm going to put that there. In exactly the same way, I plug in A, these go away. Any suspicions about what's going to happen with the third derivative? Give it a try. When I do the third derivative, C3 term is now the constant. C4 term now has an x minus a to the first. And everything after that's going to have at least one x minus a in it. So when I plug in a, all of those cancel. I'm just left with that first number. All right. Hang on just a minute. 1 C1, 2 times 1 times C2, 3, 2, 1 C3. If this pattern persists, then my fourth derivative should be, and that makes sense if I take one more derivative, this is the piece with the constant. It turns out this is going to persist. Always, no matter how many derivatives I take. And then my brain says, wait a minute, 4 times 3 times 2 times 1, that's a factorial. 3 times 2 times 1, that's a factorial. Wait a minute. Coefficient that went with C0 was just 1, right? Right, when we were talking about factorials, I made a point to mention that 0 factorial is 1. That fits the pattern 2. The 0 derivative would be f of a. Wait a minute. Let's use this formula to solve for Cn. If I don't know a geometric way to get a power series, I don't have to, as long as I can take derivatives. If I have a function and that function has a power series, then the coefficients of the power series can be determined by taking the derivatives of the functions and dividing by the factorials. Any series of this form is called a Taylor series. And this particular expression is called Taylor's formula. And when we build this from a function, we're creating a power series, which is called the Taylor series for f centered at a. Now, this particular idea was not independently discovered by Taylor. Several other people working on very similar projects at the time. And one of them, a gentleman by the name of Maclaurin, only wanted to work with series that were centered at 0. And if that A value is 0, then the only thing that changes is the number in here and the number subtracted. So Taylor and Maclaurin actually worked on these ideas at the same time, and Taylor's work generalized Maclaurin's work to lots of other spots. I know, I've spent the last 15 minutes doing nothing but theory, which is kind of annoying. So we need at least one example to do a lot of. But before I jump into my example, questions? Okay, I'm going to give you my favorite power series in the entire universe. I'm actually going to do a Maclaurin series. And I want to do it for e to the x. Now, advantage. I'm going to take the derivative of e to the x over and over and over and over, and I'm going to plug in 0 every time. But I need to keep track of the order. I need to keep track of the n. So I'm going to build a little table here. And with this table, I'm going to write down my function. The 0th derivative of e to the x is e to the x. I took no derivatives. What's the first derivative of e to the x? What's the second derivative? This is going to get boring really quickly, isn't it? Hot damn. As a matter of fact, every derivative of e to the x is e to the x. I like that one. What happens when we plug in 0? Because this is a Maclaurin series, I plug in 0. What's e to the 0? Every time. Yes? No matter what derivative I took, every derivative's value is 1. Which means I have a power series expansion that I can write using Maclaurin's idea. But all of those derivatives, every single one of them, is a 1. This is an amazing sentence. If there is a power series for e to the x centered at 0, it's got to look like that one. We made the assumption that this converged on some interval. Now I get to ask you, what interval does that power series converge on? How do I find an interval of convergence? I'm going to do the radius convergence thing. Ratio test. Whip out the ratio test. Tell me what you get. Again, Jacob? Because when I take the one out of the bottom and flip it over, I'll have an n factorial on top and an n plus 1 factorial on the bottom. Leaves me just the n plus 1 on the bottom. X to the n plus 1 over x to the n leaves me just 1x on top. That's the only part that needs the absolute value, because n is a big number going to infinity. It's going to be positive. What's this limit? What's that mean? About my radius and interval of convergence. Because for every value of x, L is less than 1. Where L is less than 1, my series converges absolutely. This converges absolutely for all x. And the interval of convergence goes from minus infinity to infinity. So not only do I have a Maclaurin series for e to the x, I know that this particular Maclaurin series should be good everywhere. Well, yeah, but Jacob did that in his head, or at least didn't tell me about it when he said what he was saying out loud. But yes, you have to, if you want to, write down, pull it out, flip it over, do the canceling. Absolutely. The amount of simplification you do on the piece of paper only matters to me if you make a mistake in the process, so that I know where the mistake was made. The more you write down, the better it is. But this step from here to here is 100% correct. And so I was okay not writing down the interim step. Other questions? You'll pardon my bluntness. This is amazing. Why? Why is this amazing? Because e to the x is a transcendental function. You've heard that way back in algebra class. We mentioned this idea of transcendental as something that couldn't come out of a polynomial. No matter what you do, there is no polynomial whose answer is e. A series is an infinite polynomial. And now I have a connection between the universe of polynomials, things I can never get from polynomials. By using infinity, I have transcended the limits of algebra. Now, people, I'm a geek, so to me that's a big deal. All of a sudden, I transcended the limits of infinity. Sounds completely dumb, doesn't it? But in terms of what analysis gives me, that makes this expression very powerful. Instead of doing e to the x, I can use an infinite polynomial. Ladies and gentlemen, your calculator never uses e. The button for e to the x is a lie. Your calculator uses this power series. Every computer program in the world doesn't have e. It has this power series. As far out as we need to go to be accurate. Questions? Okay. The problem I have with all of the work we've done is back on the previous page of my notes. If I have a power series, then this is what it looks like. There's just one problem here. And Taylor was told when he was talking about this work, well, you've said if there's a power series. How do I know whether or not there is a power series? How can I take that if and make it, I'm sure there is a power series, and this is the right one? Now, this sounds like a really philosophical question. And in one sense, it is. In another sense, it's a very practical question. A lot of people in theoretical math get caught up in the idea of, oh, I've got all these nice properties, I've got all these nice things, that nobody ever says, hey, can you give me a guarantee that this works for something? It's an apocryphal story. I don't know to whom it happened, but it's a cautionary tale to everybody working in math. There was a gentleman who wrote literally a 250-page paper describing, here's a collection of functions with all of these properties, and here are all these nice results, and this is groundbreaking, important work. And then he was asked, give me an example of a function in the set you've described. And it turned out the only function that satisfied all the criteria he'd worked out was 0. And then all of his arguments basically became, you know, when you add 0, stuff doesn't change. When you multiply by 0, you get 0. 250 pages to say 2 sentences. That sucks. So I hate the word if at the start of a process. I want to know that I have such a series. Taylor said, what you're really asking me to prove is that the convergence is good enough. That knowing that we have a series and that it converges by the ratio test is enough to make this work. So Taylor said, what I really need to show is the way that the derivatives behave gets small. So really it comes down to, can I find a bound for the derivative? Not just any derivative, the general derivative, fn of x. And Taylor actually showed if the nth derivative is bounded somewhere. Actually, he went a step further and looked at the n plus first derivative. And he said, we'll look at some interval centered on our series center. So look between negative d and positive d, to the left and to the right of our center. And he said, if we're bounded there, then the remainder, wait a minute, I've heard that term before. The remainder is everything from the nth plus 1 term on, must be less than or equal to m over n plus 1 factorial x minus a to the dth power. Oop, not dth power, n plus 1 power. I got to copy crap down properly, sorry. Now, why does this matter? Well, take a look at that right-hand side. M is a constant. And if I look at the remainder, then as n goes off to infinity, this bottom gets absolutely huge, doesn't it? And that means that my remainder goes to 0. That's what makes the convergence good enough. That this function, f of x, is closer and closer and closer to the partial sums. That's the way converging works, right? But we're not converging to a number, we're converging to a graph. Remember the picture I showed you the other day? Of all of those partial functions? Let's recreate that picture. So, first graph is e to the x. Then, I'm going to graph some polynomials. Ready? I'm going to graph 1 plus x, 1 plus x squared. Oh, not 1 plus x squared. 1 plus x squared over 2, right? That would be the first 3 terms. Then 1 plus x squared over 2 plus x to the third. Oh, not up there, down there, over 6. Right? That's the first 4 partial sums. I'm going to graph this. There's my graph of e to the x. I want to look much closer in. So I'm going to zoom in right here. There's the graph of e to the x. 1 isn't a very good estimate, is it? 1 plus x is much closer. That's even closer, isn't it? Notice how the part where the curve of the polynomial overlaps the curve of e to the x keeps getting bigger. We went from just barely touching it to overlapping on a small interval, then the parabola overlaps on a larger interval, and then the cubic equation overlaps on an even larger interval. I did a 4th equation, 5th equation, that grows and grows and grows, doesn't it? Because the leftovers, the remainder, gets small. And so my convergence doesn't happen at one point, it happens all the way across the graph. as I take more and more powers of x, the graphs get closer, closer, closer to the graph of e to the x. And notice some of them came from above, and some of them came from below, but they all close in to the whole picture, not just to one number. And so our definition of convergence was expanded by Taylor, and all of a sudden we had this new type of converging in graphs. Now, Taylor didn't actually do this visually. He did this strictly algebraically, and he called this sort of thing uniform convergence. That is the last time you will hear me talk about that term here in this class. I'll save it for the theory class, real analysis. I claim this is true for our function e to the x. Now, no matter what derivative I take of e to the x, I get e to the x. So, here's an interval from minus d to d. Because remember, our series was a Maclaurin series, a is equal to 0. If you were graphing e to the x on Gesundheit, this piece of graph paper, where would the largest possible value for e to the x occur? The largest y value? Between here and here, what's the graph of e to the x look like? Because the right side is up, the left side is down. That means I have an upper bound for the derivative, don't I? The derivative is always less than or equal to the y value at d. We found the biggest spot on this graph. So this is my value of m. Since our a is 0, I don't need to write x minus a, I just write x instead. Now, Taylor said, I know that no matter what, that is never bigger than d, right? Last time I checked, we're on this interval, so the biggest possible value for x is d. That should be a less than or equal to, not an equal to. Now, I get to ask you a question. What's that limit? Ew. Wait a second. I have a power on top. I have a factorial on the bottom. We've done this before. Which wins, the factorial or the power? Say again? The factorial. Factorials get absolutely enormous by comparison to powers. We even did n to the nth over n factorial, right? Oh, this is going to be insane. But if the factorial wins, then the bottom of this fraction is bigger than the top. What's my limit? 0. And that was exactly the conclusion that Taylor said, hey, if this remainder's limit is 0, you must have a power series expansion. And the Taylor series must work. And all of a sudden, all of this work in calculus and in analysis and in sequences and series, everybody said all of this stuff works for polynomials, and every function that's not a polynomial can be arbitrarily close to a polynomial. I just need enough powers. This works. Son of a... This works for any function, provided I know how to take the derivative of that function. And that means that all of the work I love to do in calculus about derivatives and integrals can now turn into work on series. Since I know how to take the derivative and the integral of a polynomial, I can do this. I'm going to give you a problem that I told you last year was impossible. I don't know how to do that. I do not know what the antiderivative of that function is. As a matter of fact, there is no nice antiderivative for that function. But e to the minus x squared can be turned into a power series. And not just any power series, a variation on this power series. Because if I know e to the x is this power series, then I know what e to the minus x squared is. I just put the minus x squared everywhere I see an x. Let's play the trick we were playing on Monday. What can I do with that minus x squared there? How can I rewrite that the way we did on Monday? Or maybe it was Friday last, but I think it was Monday. But if it's squared to the n, then it's just 2 times that, right? Perfect. This integral just became the integral of this series. And I know how to integrate a series. What do I do? Integrate. Oh, I forgot to write down my dx. I integrate term by term. Minus 1 to the n over n factorial. What's the antiderivative of x to the 2n? That's it. And that's the only version of the antiderivative that I know. I have more to say about this, lots more to say about this. I have some other examples that I am going to do tomorrow. So I will see you all then. I hope you have a wonderful rest of your day. And then on Friday, we're doing question and answer day, and we will have finished this chapter. What does that mean? There's an exam coming. The exam is next Wednesday. The review sheet's already up. And the formula sheet that's attached to the review sheet is the formula sheet on the exam. I will see you all tomorrow. Have a wonderful rest of your day.